Hello and welcome. My name is James Edward Gray II, and you are watching Codalyzed. Today's topic is state machines and how we can use them to simplify our code while increasing robustness. I believe state machines can improve a lot of programming, so it pays to gain an understanding of what they are and how they're used. Today we'll do that by dissecting a state machine library to see how it works. Let's dive right in. The library I want to dig into this time is called Micro Machine, which, if you ask me, is a great name. First, I did play with the tiny vehicles of the same name when I was a kid. Even better, though, this code is exactly what it says on the tin, a tiny tool for building state machines. Just like last time, the only steps I've taken at this point is to pull the code off GitHub. Assuming you have Git installed, that's as simple as running this command. A few seconds later, you should have a new directory with the code inside. I've moved into that directory, and now I'm going to open the code in my editor of choice, Emacs. I'm pretty much planning to follow the same playbook that I used in the last video. Get the test running so I can actively read the code, scan the README file to get a lay of the land, and then dive into lib. I have noticed that this project includes an examples directory, so I'm going to peek in there after I finish with the README to further my understanding of how this code should be used. The moat library that I examined in the last video was by the same author, and it had a similar structure, so I'm going to start by assuming that it works in a similar way. If that's true, it's probably tested with the Codalyzed library, and the makefile is probably set to run those tests for us. I have Codalyzed installed from when I made the last video, so let's just see if I can get really lucky and run the tests. Perfect. We've got our safety net in place and we're ready to start exploring. Let's see what the README has to say. Okay, so what do we see here? Well, the description adds the term finite, while I have so far just been saying state machine. Finite just clarifies that there are a limited number of states the machine can be in. Infinite state machines are much less practically useful, so you'll find most references to state machines are really about finite state machines, and the two terms are generally interchangeable. Then we get to the good stuff. That first code example in the usage section is the reason I like to start with the README. I suspect it shows us most of what we need to know. We can see how to create a new machine and place it in the initial state, how to add transition events and specify both which states they affect and what the resulting state will be, and how to trigger state changes when needed. This is what state machines do. They play gatekeeper for a list of transitions, ensuring that the rules are always followed and that the code never ends up in an unspecified state. Next, we see something about syntactic sugar that I'm just going to ignore. I'll stick to the easy way they've already shown me until I have a reason not to. We can see there's a way to check state changes before you actually trigger them. That could be handy. You can also make state changes fail loudly. Good to know. Then we see what I suspect is the last piece of the puzzle. Most state machine implementations I've seen give you some way to run a bit of code when certain states are entered. It looks like Micro Machine does this with an on method that takes a block. Then when the named state is entered, the block is called. We also see here that you can provide some code to run when any transition happens. Nice. The last line of the usage section reminds us to check out the examples. We will definitely do that. This is an interesting section on using Micro Machine with active record. Let's read a bit. The most popular pattern among Ruby libraries that tackle this problem is to extend the model and transform it into a finite state machine. Instead of working as a mix-in, Micro Machine's implementation is by composition. You instantiate a finite state machine, or many, inside your model, and you are in charge of querying and persisting the state. Here's an example of how to use it with an active record model. Okay, so the gist here is that we build a machine and provide the transition rules just as we would without a database involved. Then we can provide the needed methods to trigger state changes. Now, the trick is to make sure that the current state gets persisted in the database. To do that, this code hooks into Active Record's lifecycle and arranges for the state to be copied into a persistent field before a save happens. I glossed over this before, but that field is also used when setting the initial value for the state machine. It mentions that this looks verbose, and I suppose that's true, but I really like how I can follow what's going on here. I can see when things change and why. I can see how persistence is handled. I can understand wanting an Active Record plugin to handle more of the details for you, if that's your preference. But I still think examples like this are valuable, if only in showing us how the process can be structured. Looks like we have another example below. So the difference in this one is that a callback on the state machine updates the field anytime a transition occurs. I think I prefer that approach because we then know that the active record field will always be in sync with the state machine instead of just being brought up to date when a save is about to happen. It looks like that's all the meat in this README. Time to check out those examples. I hope I have the basics and callbacks at this point. Let's skip straight to the advanced example and see if we pick up anything new from it. I don't really see anything new there. Perhaps the use of an any callback is considered advanced? Not sure. These files may come in handy when we're playing with the code, though. It might be nice to have these executable examples that we can tweak as needed to try things. Alright, before we move into the code, let me make up a few examples to set up what we're going to be seeing. I confess that I had an ulterior motive for choosing to dig into Micro Machine for this video. I think state machines are an underappreciated tool for programmers. A lot of people I talk to either don't really know what a state machine is, or don't really know what they're used for. I've already told you that I consider a state machine to be a collection of the states that a system can be in, and the rules that govern when we switch between them. But what does that actually mean in practice? Let's play with a simple example for a few minutes. Say that we have an object to represent an order in our system. The idea is that we'll move order through various statuses as different events happen. Here's some sample usage. Don't worry about that first blank line and nil. Emacs does that when I ask it to move the code from the buffer I'm working in to the REPL. In the rest of the code, you can see how we update the status. Obviously, a real order object would have more details, but we're just focusing on this one aspect. Now, it may not look like it, but this is a state machine. It's a pretty terrible one, but it is one. Why do I say it's terrible? Well, it's missing the legal list of states and the rules that govern transitions between them. This means that it's easy to make mistakes. For example, say that you don't remember that we're calling the status after a payment is collected paid. You might accidentally code up something like this. This can seem reasonable, but code down the pipeline looking for paid won't catch this order. In fact, it may not show up in any queries or reports if they are only checking for expected statuses. I'll be honest though, I don't think this example is very realistic. I don't often see code like this in the wild. Let's take a look at a more realistic version of the same thing. I do see plenty of code like this in the wild. In fact, the use of booleans or timestamps to represent a process like this is a huge hint that you have a state machine hiding in the code. We use this code similarly to the previous version, only we set timestamps and let status recognize those changes. Clearly, this is better. We can see the states just by reading the status method, and we now have more information about when state changes happened. But honestly, this code still has similar flaws to the simpler version we looked at before. What state is this object really in? According to status, we've shipped this order, but did we get paid? It's not clear. We probably never expected the code to reach this point, but experienced programmers know all too well how often the unexpected becomes reality. If we want to prevent scenarios like this, we'll need to code more defensively. Let's look at one more example that does that. The difference here are the three methods added to manage the state changes. Together, these methods make up the rules for transitioning from one state to another. More specifically, the calls to fail mostly prevent the object from reaching an unplanned configuration. If we try, we'll get an error. This ensures that we move the object forward as planned. This is a more effective state machine. It manages the states an order can be in. In the object's code, we call those the statuses of an order, but that's just a domain-specific alias. Some objects may even make use of more than one state machine to manage multiple independent processes they are going through. Okay, we've established what a state machine is and how it works. Now the real question is, how often do they come up? My answer would be probably more often than we think. Consider this diagram of a typical online checkout process. In this case, we start the user on a page where they can fill out their shipping information. It's expected that they'll then move on to billing details and finally confirming their order. However, from any page, they're allowed to jump back to previous pages and make changes. This is just another state machine. Where you can go, or which states you can transition to, is dependent on which page you are currently viewing, or which state you are in right now. Both of my examples have been about shopping systems, but state machines show up in a lot of places. I've already mentioned that the use of multiple Boolean values or timestamps can point to state machines hiding in an object. These objects often model processes that move through a series of stages. Odds are you've seen such things before in your own projects. As for website navigation, consider friending or following someone on a social media site. You send a request, they act on it, then you're notified of their response. Generating reports. You enter some criteria, a report is built, and it's somehow delivered to you. Or a site API where you can list items, see details on an item from the list, or make changes to the item you have viewed. You may not always need to represent these state machines in code. For example, the server of the hypothetical API may not follow each user through that imagined chain of requests. Then again, a client for that API might do exactly that. A lot of things we tend to add to apps as background jobs can be handled as state machines. I think this is true because you generally want at least 3 states to make a state machine worth the effort, and a background job is usually a minimum of 3 states. Queue some work, do the work, and deliver some feedback. Some examples include resizing images. Queue the file, handle the scaling and possibly cropping, and push it to a content delivery network. Database imports, bulk mail senders, GitHub's fork repository action. State machines also come up a lot in parsing. Regular expressions can be translated into state machines that move through the conditions of a successful match. I can match an R at this point, or the end of the input. Markdown parsers can keep track of which level they are currently at to know what changes in indentation mean. At the root of a document, they could signal a code block, but inside a list, it could be a nested code block or a no-op used to align the list elements. You get the idea, but before I end this commercial, let me tell you what some other programmers you might respect think. Avdi Grimm has said more than once that he's still waiting on a programming language to appear that has state machines built into every object. Dave Thomas once told me, if you view the world through functional glasses, where every program is just a set of nested transformations, then state machines are the overarching way you design. Food for thought, eh? Even if you're not ready to go all in on Dave's view just yet, I hope I've convinced you that state machines are common in what we do. This means spending a little time getting the hang of them can pay significant dividends in your future work. One way to do that is to see how a state machine library works on the inside. So let's get back to that now. Okay, let's open up the code. I love these error classes we see right at the top of the code because they make use of cool Rubyisms to accomplish a task in a better way. Let's look at what they do by seeing what they're equivalent to. First, I'll remove one. That should break the test. Excellent, it does. To fix things, let's add a class definition that means the same thing. That gets the test going again. But it's not as nice in my opinion. First, it's an empty definition. It exists just to create a new type of error for some code to fail with. It's also kind of this awkward beast that I can't figure out how to style. As is, I've just opened and immediately reclosed the definition. Would it be better with a blank line added? Do I need to put something extra on that line, like a comment ensuring others that I intended to leave it blank? Do I use a semicolon and collapse the definition to a one-liner? Even in this form, it's still not super clear if you ask me. The important detail, the name, invalid event, is hidden behind a noisy keyword. That's why I love the solution the actual code uses. It begins with invalid event equals, so it's clear that it's creating exactly that. Now, the direct assignment works because of two key details of the Ruby language. First, let's talk about classes. We know that almost everything in Ruby is an object. As an example, this pair of brackets creates an object of the array class. What we must realize is that the array class itself is also an object. It is an instance of the class. If we realize it's just another kind of object in Ruby's world of objects, it's not too surprising that we can create it with a normal constructor. You can do this even for objects that Ruby bakes in some syntactic sugar for. The constructor for class takes an optional parameter for the superclass. You can even pass a class definition in a block, though we don't need that for this case. All of this explains the right-hand side of the assignment we are breaking down. Now let's discuss the left-hand side a bit. In Ruby, classes have a name. That name is set the first time a class object is assigned to a constant. Notice how even the REPL started referring to my class differently the instant it had a name. You can think of a traditional class definition as combining the two steps of calling the class constructor and assigning the resulting object to a named constant. Enough about clever error subclassing. Let's look ahead. We've gone from an idiom I love to one I don't care for. ATTR is similar to ATTR reader, ATTR writer, and ATTR accessor, but I don't see it used too often these days. There are probably some good reasons for that. I tried to look up the documentation to verify my memory of this feature, but it looks like we're on our own. Let's ask Ruby what it does. So from just that, it seems equivalent to ATTR reader, but if I remember correctly, it can also take a magic flag. Yeah, that makes it function like ATTR accessor. If there's a way to get ATTR writer only behavior, I don't know what it is. That makes sense to me. I pretty much never want the writer without the reader. Now, honestly, I don't know if it can handle multiple attributes at once. Let's try it. Yep, that works. So can we get multiple attributes with writers like this? Ugh, no. This is getting twisty, isn't it? Okay, let's recap what we know about ATTR. It functions similar to ATTR reader and sometimes ATTR accessor. It's undocumented. It makes use of a non-obvious magic Boolean flag, and it's less capable than the explicit methods. I would say these are the reasons the explicit methods have become more popular. They tell a reader of your code what's going on with no guesswork required. I've spent a bit of time here examining obscure corners of the Ruby language, and I want to get back to talking about state machines. I will say, though, that I think it's worth considering when language constructs can make your intent more obvious. I always try to remember that the primary purpose of code is to communicate with the reader. To that end, I'm going to switch those ATTR definitions to use ATTR reader instead. Let's make sure that still works the same. Great, it does. Now let's get into how this library really works. Internally, this library tracks three things: the state we are currently in, a map of all possible transitions, and a map of any callbacks to run when a new state is reached. These latter two bits are both implemented using Ruby's hash, and the callbacks hash is defined with a custom default handler that we should probably discuss a little bit. There are multiple ways to set a default value for a hash. In the simplest form, you can just pass a value to the constructor. In a case like a default of 0, this generally works out fine. The reason is that you will change the default by replacing it. That doesn't work well with array for a couple of reasons. Check out this example. One issue is that with an array, we aren't as likely to replace the value as we are to just modify it. This isn't a problem with numbers because you can't modify numbers in Ruby. As you can see, every time we change the array, all future references to it picked up that change. That's because there's only one array in play here, the one we handed to the constructor. We just keep getting references to the same object, and we're adding contents to that shared instance. Also note the other issue. Our hash still technically has nothing in it. Again, because we're not replacing the values with some form of assignment. We fetch and modify the default object, but we don't actually set some key in the hash to a value. The solution to these problems lies in providing a default block for the hash. This block will be run every time a default value is needed, so a partial fix would be this. Because the block is run each time we need a default, a fresh array gets created, and we're no longer modifying the same instance over and over again. That fixes the first issue. However, the second issue remains. We're still not assigning to the keys. We commonly fix this in Ruby by using the arguments passed to the block to perform the assignment at the time a new default array is generated. This resolves both issues we originally noted, but it adds a new minor issue. That is that a key is now assigned when we just fetch some value, even if we don't modify it. If we want to prevent random keys from being added, we need to check if they are already present first, using something like include. Getting back to the library code, it kind of surprises me that only one hash was defined with this fancy default. If I remember the README right, the transitions for hash has hash values in it. For some reason, those aren't defaulted in. Perhaps we'll be able to better understand why as we move forward. Okay, so the next two methods just give you ways to stick things in the two hashes we've been discussing. On adds to the callbacks hash using the exact array modification technique that we just analyzed. When is more of a direct assignment, I guess because it doesn't have the special defaulting logic. I'm still not sure why there are two different approaches here. Alright, it looks like the next three methods are where the action is. Trigger is the main workhorse method, but you can see that it immediately calls trigger ? To find out if a state change is currently possible. Let's start by understanding that helper. Trigger ? Opens with a guard clause to make sure the system has some transition rules for the requested event. If we don't know what the event is, it cannot be a legal transition by definition, and it's time to toss an error. Now, if we know the event, it might be a legal transition. We can find out by checking to see if we have any transition for our current state when event occurs. It looks like that test is made here by just checking the hash and using the ternary operator to force a true-false return value. I wouldn't say this is the usual idiom for forcing Boolean values in Ruby, but double bang is more common, I think. I assume these transformations are pretty obvious as I've shown them here with Booleans, but consider non-Booleans used as truthy or falsy values. So one bang, or not, converts any object into its opposite Boolean value. Another bang yields the opposite of that, or the original truthy or falsy value as a Boolean. We could argue whether this is cleaner or not, for sure, but it's pretty common in Ruby code. So let's edit the method a bit. That should still pass the test. It does. Fine, but I still wouldn't do it. The fact is we can take a hint from the line above and use an even more clear method call. I feel that shows the intent better than the ternary operator or a double bang, and it seems the test still pass. Alright, we get that trigger ? Tells us if a transition is possible. Now let's zero in on trigger. This is the biggest method, but it's surprisingly straightforward. It first uses the method we just deciphered to figure out if the transition is legal. Assuming it is, this code does three things. Move to the new state indicated by our transition rules. Trigger all callbacks for our new state, plus the magic any callbacks that always apply, by iterating over the combined list and sending the call message to each block. Return true to indicate that we did transition. If we don't transition because trigger ? Said it wasn't legal, false is returned instead. These return values let the caller know if our internal state has changed. If you would prefer a less subtle notification, there's the trigger bang method. So this just delegates to the method we just looked at to test the transition, change state, and invoke any callbacks with one simple twist. If the state change isn't legal, throw an error. This forces the calling code to deal with the fact that this change isn't permitted. I feel a bit like this method duplicates the return value from the normal trigger method, and that makes me want to tweak it a bit. I think I'd prefer this version using Ruby's control flow Boolean operators. It seems to read a little more directly with our intent. Trigger this event or raise an error. The test still passed this way. Now that I've seen that, I realize the last method has the same issue. Let's go back. See how that method also repeats the false return value from trigger ? It's the exact same layout as the one we just fixed. I think we should change this one in 2 steps though. First, let's extract the state changing code. The test should still pass like that. And they do. Now we can rework trigger. It's a small change, but it does make the trigger methods more similar in how they work. I think I like it. The test still passed this way as well. Enough refactoring. We've got a few methods left to examine, and it looks like the next 2 enumerate the keys and values of the transition rules hash. Okay, so events are keys in the transitions hash. They are the actions you can pass to trigger to cause the machine to change state. The next method is a little twisty. It seems to pull the values in some form, but I'm not clear why it's mapping the event names through the hash and why 2A, flatten, and unique are involved. I think I want to see an example of what the transition rules hash actually looks like. Let's go back to one of those example files and see if it can help. Perfect. This file builds up a simple machine, so we can use it to peek inside of one. It tells us how to run it. Let's try that. Well, that's no good. What's going on? Ah, it's an examples directory, not example singular. We'll fix that and try again. Great, we have something we can run. Now let's modify it a tiny bit to show us what's under the hood. All I'm doing is loading Ruby's standard pretty printer library and asking it to show me the hash after it's been constructed. I also added a call to exit so we won't be confused by any additional output. Let's see how that looks. Okay, there's our hash. The keys are event names as we expected: confirm, ignore, and reset. Now we can see that the values are nested hashes that list state transitions that can happen when an event arrives. So when we get the confirm event, we move from the pending state to the confirmed state. If we weren't in the pending state at the time, nothing happens. However, the reset event can move us from the confirmed or ignore states back to the pending state. I think I'm ready to see that states method again. It's still weird to me why it maps over the event names, but it seems to be grabbing those value hashes and turning them into arrays. What happens when you convert a hash to an array? Let's ask Ruby. In case you aren't aware, the underscore is replaced with the value the last expression evaluated to in a Ruby REPL. Okay, so 2A gives us an array of arrays. Flatten removes the nesting, and unique takes care of state names possibly being mentioned in several rules. The end result is the list of all states mentioned anywhere in any transition rule. I understand it now, but I still don't feel like we need to bother with events. Let's try and edit. Does that still pass the test? Yes, it does. Honestly, I think we could golf it down a little more even. I believe hash has a flatten method that takes it straight to a one-dimensional array. If we flat map over those, we'll end up with a single array, and then we can unique that. That removes a step and some allocation of objects we don't need. And it still passes the test. I doubt I would really use that though. The flat map plus hash flatten combo is probably harder to puzzle out than what I have commented out. I couldn't even come up with it until I had seen the whole process. Again, I would let readability win. It's probably worth mentioning that I'm not making all these edits because I think the code is gross. Sometimes I may land on a change that does the same thing and that I think improves the code in some small way, but that's more of a happy accident than a goal. My goal is simply to understand how this code works. I'm trying to engage as much of my brain in that process as I can manage. By using all of the tools at my disposal, the README, example code, or REPL, and tinkering to see what does and doesn't break, I can load the code into my head and understand how it works. Speaking of understanding how it works, let's go back to that hash that didn't have the special default block to see if it makes sense now. The value hashes that map state changes come in as the transitions parameter of the when method. That's just directly assigned to the transitions for hash. It's not added to a created on demand default hash. What are the implications of that? Well, one is that you can't define an event with multiple calls to win. Each time you call it, the state changes are fully replaced, so you must provide all the definitions in one call. Another potential issue I can think of is that you could break the system by not passing a hash. It's often true in Ruby that ignoring the expected types will hurt you, but this is a case where I believe we'll get a weird error coming from a different part of the system than where the problem really is. Yeah, that could happen. I'm not sure it really would, and we can just insert a guard clause if we're truly concerned. Now I expect to get a more helpful error message. Ignore those warnings, they're just from me reloading the code. At least now the error message points to the real problem and it tells you what went wrong. This is probably over paranoid though and not really needed. But the tests do still pass. Okay, let's check out the final method. So it's a simple shortcut to test the current state. Yuck, don't do that. I can think of a few arguments against it. First, we can already access state, and if we just test that, our code will read better because it will say exactly what it does. Second, operator overloading should only be used in super special cases where they clarify intent. One reason for that is that they are all but impossible to Google. This case does not clarify intent. It actually changes the meaning of equals equals for these objects. That leads to my final complaint. What if you really need to test the equality of the machines themselves? Here you need to define a non-standard method to do that. We've reached the end of our exploration of the micro machine library code. I'm not going to bother going through the tests this time. I had a quick glance at them and they don't really add anything to what we have unearthed already. They are solid tests though that thoroughly specify the library's behavior, so check them out on your own if you're interested. However, let's revisit an earlier example before we wrap up this video. Do you remember the sample order class that we were playing with when we discussed what state machines are? Let's return to that for a moment. What would it look like if we rewired this object to use a real state machine library, like Micro Machine? Let's make the changes. The main change is just that we internally build a state machine and delegate everything to it. We let the state machine also handle updating the timestamps for us using a callback. This fixes a minor issue in the old code where it was possible to set timestamps, so it seemed that a later state happened before a previous one. This is also a decent example of how callbacks can be useful. If you want to lock in some code to run no matter when or where a state change is triggered from, if you need to notify some external code when state changes happen, or if you just want to share some code across multiple transitions, callbacks give you a built-in system for accomplishing such things. I must stress that I find this code far easier to change. If we needed to add a new status to the old code, we would need to add methods and variables, then go through all of the fail statements, updating them to handle the new transitions. That would be a tedious process, and we could easily make mistakes. But with the state machine object, we just list the possible changes, and the machine will ensure our rules are followed. Anyway, this code works pretty much the same in practice to what we had before. This concludes our tour of the Micro Machine library and state machines in general. Thanks for supporting Codalyzed. I hope you'll join me in the future for more code analyzing adventures. See you then.